Hello there. Tonight we're going to drift away into the cosmos, into the gentle rain of starlight that falls silently through the darkness above us. We're talking about meteor showers, those celestial displays that have been quietly painting the night sky for millions of years. Some are brilliant and dramatic, streaking across the heavens like cosmic fireworks. Others are subtle and soft, barely visible whispers of light that fade before you can point them out. But each one carries with it a story that stretches back to the birth of our solar system. Ancient tales written in dust and ice that have been traveling through space longer than life has existed on Earth. These shooting stars aren't really stars at all, but tiny fragments of cosmic debris that create moments of beauty so fleeting, they remind us to pause, to look up, and to wonder. If you enjoy drifting off to the gentle mysteries of space, feel free to like and subscribe or simply share your thoughts down in the comments. It helps others find their way here too. But for now, let these cosmic visitors carry you into rest. And if you're ready, let's begin our gentle journey through the most peaceful celestial phenomena in the night sky. Most meteor showers return like old friends on the same date every year. The Perseids arrive faithfully each August, the Geminids grace December skies, and the Leonids dance through November darkness. This celestial calendar has been keeping time for thousands of years, long before humans built clocks or marked seasons on paper. Ancient civilizations noticed these patterns, weaving meteor showers into their myths and using them to track the passage of time. The reason for this reliability is beautifully simple. Each meteor shower occurs when Earth passes through the orbital path of a comet, like walking through an invisible trail of cosmic breadcrumbs scattered across space. These trails can persist for centuries, gradually spreading out but maintaining their basic shape and timing. As our planet follows its yearly journey around the sun, we encounter these debris streams at predictable intervals, creating the same spectacular light shows generation after generation. There's something deeply comforting about this cosmic punctuality, knowing that the same meteors our ancestors watched are still putting on their gentle performance in the darkness above us. The dust that creates meteor showers is smaller than you might imagine. Most meteors are formed by particles no bigger than a grain of sand, some as tiny as a speck of dust you might brush off your sleeve. These minuscule fragments travel through space at incredible speeds, often moving faster than 20 miles per second when they encounter Earth's atmosphere. Despite their tiny size, their tremendous velocity transforms them into brilliant streaks of light that can be seen from hundreds of miles away. The glow isn't the particle itself burning, but rather the air around it, heating up and creating a luminous trail as it passes through our atmosphere. Most of these cosmic visitors completely vaporize before reaching the ground, their entire existence compressed into a few seconds of gentle radiance. It's remarkable to think that something so small can create such beauty, like nature's own version of fairy dust scattered across the night sky. Meteor showers appear to radiate from specific points in the sky, giving each one its distinctive name. The Perseids seem to emerge from the constellation Perseus, the Geminids from Gemini, and the Leonids Ra from Leo. This diam point is simply a of perspective trick, like looking down a long straight road where parallel lines appear to meet at the horizon. In reality, the meteors are traveling on parallel paths through space. But from our viewpoint on Earth, they appear to diverge from a single point among the stars. This creates a beautiful fan-like pattern across the sky, with meteors streaming outward in all directions from their celestial origin. The radiant point slowly moves across the heavens throughout the night as Earth rotates, creating an ever-changing display that shifts and flows like a cosmic fountain. Understanding perspective trick. This makes watching meteor showers even more peaceful, knowing that you're witnessing the geometry of space itself, painted in light across the darkness. Some meteor showers are gentle whispers, while others are celestial symphonies. The quadrantids in early January can produce over 100 meteors per hour during their peak, creating an almost constant display of falling stars. The Geminids in December are known for their bright, colorful trails that seem to hang in the air longer than most meteors. The Perseids offer a perfect balance, reliable and steady, with occasional brilliant fireballs that light up the entire sky. Then there are the quieter showers like the Draconids in October, which typically produce only a few meteors per hour, but are known for their slow, graceful paths across the heavens. Each shower has its own personality, its own rhythm and intensity. Some years bring surprise outbursts when Earth passes through a particular point in space. Early dense part of a debris trail, creating unexpected meteor storms that can fill the sky with hundreds of shooting stars. But even in quiet years, there's something magical about lying back under the stars and watching these cosmic visitors drift silently overhead. The parent comets that create meteor showers are ancient wanderers with stories spanning millennia. Comet Swift-Tuttle, which gives birth to the Perseid meteors, takes over 130 years to complete one orbit around the Sun. During its journey, it sheds tiny particles that spread out along its orbital path like a cosmic contrail. These particles continue their journey through space long after the comet has moved on, creating the debris stream that Earth encounters each August. Some parent comets haven't been seen for centuries, yet their meteor showers continue to grace our skies with clockwork precision. Others, like Comet Halley, are famous visitors that return regularly showers, though their meteor, the Orionids and Eta Aquariids, occur when Earth passes through different parts of the comet's orbital debris. There's something profoundly peaceful about knowing that these light shows connect us to cosmic events that happened hundreds or thousands of years ago. Celestial time capsules that bring star ancient light to our modern skies. The best meteor watching happens in the quiet hours before dawn, when the sky is darkest and Earth is rotating into the debris stream. This is when your location on the planet is facing forward in Earth's orbital motion, like the front windshield of a car driving through a snowstorm. The atmosphere is usually calmest during these pre-dawn hours, with less turbulence to interfere with the meteor's gentle. Light pollution from cities can wash out all but the brightest meteors, so the darkest skies reveal the most shooting stars. But even a few meteors glimpsed from a backyard can be deeply satisfying. Brief moments of connection with the cosmos that remind us of our place in the vast universe. The quiet ritual of meteor watching, lying back under the stars with a blanket and perhaps a warm drink, creates its own peaceful meditation. There's no rush, no schedule to follow, just the gentle anticipation of the next bright streak across the darkness. Meteors create different colors based on the elements they contain and the gases in atmosphere. Green. Our meteors are common, created by magnesium and oxygen glowing as they heat up. Red meteors often come from nitrogen in our atmosphere, while yellow and orange streaks can indicate the presence of sodium. Blue meteors are less common but particularly beautiful, usually caused by calcium or magnesium at very high temperatures. These cosmic chemistry lessons paint themselves across the sky in subtle hues that most people never notice unless they're really watching carefully. The colors are often too faint for the human eye to detect clearly, appearing mostly white to casual observers. But long exposure photographs can capture these delicate tints, revealing the hidden rainbow in each meteor's brief journey through our atmosphere. Even knowing that these colors exist adds another layer of wonder to meteor watching, imagining the invisible spectrum of light created by each tiny cosmic visitor. The atmosphere plays a crucial role in creating the meteor's gentle glow, acting like a cosmic concert hall that transforms silent space dust into visible light. As meteors enter the upper atmosphere at altitudes of 50 to 70 miles above Earth, they compress the thin air in front of them, heating it to thousands of degrees. This superheated air glows with the same principle that makes neon signs light up, creating the luminous trail we see from the ground. The meteor itself rarely survives this intense heating, vaporizing completely as it sacrifices itself to create a moment of beauty. Occasionally, larger particles do make it through the atmosphere to become meteorites, but most meteor shower debris is far too small and fragile to survive the journey. The entire light show typically lasts only a few seconds, a brief but brilliant transformation of cosmic dust into earthly wonder. Different meteor showers have their own seasonal rhythms that connect them to Earth's annual journey around the sun. Spring brings the Lyrids in April, often producing moderate displays with occasional bright fireballs. Summer offers the Delta Aquarids in July and the famous Perseids in August, perfect for warm nights under clear skies. Autumn delivers the Orionids in October and the Leonids in November, sometimes creating spectacular meteor storms every 33 years when Earth passes through a particularly dense part of the debris trail. Winter provides the Geminids in December and the Quadrantids in January, though cold weather can make observing more challenging in northern climates. This natural calendar creates a rhythm to the year, marking seasons not just by changing weather, but by the different cosmic visitors that grace our skies. Each season brings its own celestial personality, its own gentle reminder to look up and marvel at the universe's ongoing light show. Human cultures around the world have watched these same meteor showers for thousands of years, weaving them into folklore, mythology, and spiritual practices. Some Native American traditions saw meteors as souls traveling to the afterlife, while ancient Greeks believed they were stars falling from the heavens. Chinese astronomers kept detailed records of meteor showers for over 2,000 years, helping modern scientists understand the long-term behavior of these cosmic events. Many cultures considered meteors to be good omens, wishes waiting to be made, or messages from the gods. This shared human experience of wonder connects us to countless generations who have lain under the same stars, watching the same gentle light show with the same sense of awe and mystery. The meteors themselves haven't changed, but they continue to inspire the same fundamental human response of looking up into the darkness and feeling both small and connected to something infinitely larger than ourselves. The study of meteor showers has revealed fascinating details about the composition and history of our solar system. Scientists can analyze the light spectra from meteors to determine what elements they contain, essentially reading the chemical fingerprints of ancient comets. This cosmic archaeology helps us understand what conditions were like when the solar system was young, billions of years ago. Some meteors contain organic compounds, the building blocks of life, suggesting that comets may have delivered the ingredients for biology to early Earth. Others carry isotopic signatures that reveal their origins in the outer reaches of the solar system, places so cold and distant that these materials have remained virtually unchanged since the solar system's birth. Each meteor shower is therefore a gentle lesson in astronomy, a natural laboratory that brings samples of deep space directly to our doorstep for study and appreciation. The silence of meteor showers is one of their most profound qualities. Unlike thunderstorms or fireworks, these cosmic displays unfold in perfect quiet, their light appearing and vanishing without sound. This silence isn't just peaceful, it's deeply meaningful. The meteors are occurring dozens of miles above us, far beyond the reach of Earth's atmosphere where sound can travel. Even if they made noise, we would never hear it from the ground. This creates a uniquely meditative experience where the only sounds are those around you. The gentle rustle of leaves, the distant call of a night bird, or perhaps just your own quiet breathing. The visual spectacle happens against this backdrop of natural silence, making each streak of light feel like a personal message from the cosmos. There's something almost sacred about this wordless communication between Earth and space, a reminder that some of the universe's most beautiful moments happen in complete stillness. Most people don't realize that we're actually traveling through meteor streams at incredible speed. As Earth orbits the Sun, we're moving at roughly 67,000 miles per hour through space. When we encounter a comet's debris trail, it's like driving through a cosmic cloud at astronomical velocity. The meteors aren't really falling toward us, we're running into them as our planet sweeps through their orbital path. This perspective transforms the experience of watching a meteor shower from passive observation to active participation in a cosmic dance. You're not just looking up at distant lights, you're riding aboard a planet that's surfing through ancient trails of comet dust, collecting cosmic souvenirs from journeys that began in solar system millions the outer of years ago. The meteors are like breadcrumbs from these ancient voyages, scattered across space and time, waiting for Earth to come sweeping through and turn them into brief moments of light and wonder. The timing of meteor showers connects us to the deep rhythms of the solar system in ways that feel almost musical. The Perseids peak around August 12th each year, the Geminids reach their maximum around December 14th, and the Leonids dance across November skies with the precision of clockwork. These dates shift slightly over centuries due to gravitational influences from the planets, but the basic rhythm remains constant. Ancient astronomers noticed these patterns long before they understood their cause, using meteor showers as celestial calendars to mark important seasonal transitions. Modern observers continue this tradition, planning camping trips and late-night viewing sessions around these predictable peaks. There's comfort in this cosmic regularity, knowing that no matter what changes occur in human civilization, the meteor showers will continue their appointed rounds. faithful as sunrise, gentle as moonbeams on water. The altitude at which meteors appear creates a unique perspective on Earth's atmosphere. Most meteors begin glowing at heights of 50 to 80 miles above the surface, in the region called the mesosphere. This is higher than commercial aircraft fly, higher than weather balloons reach, but lower than satellites orbit. From this vantage point, if you could somehow stand there, you would see Earth's curvature clearly while still being technically within the atmosphere. The meteors are lighting up in this thin, cold layer where the air is so tenuous it's almost like space itself. Understanding this adds depth to meteor watching, knowing that these lights are appearing in a realm that's neither fully Earth nor fully space, but something in between. It's a boundary layer where cosmic visitors meet our world's protective envelope, creating beauty in the transition between the terrestrial and the infinite. Some meteor showers produce unexpected gifts in the form of persistent trains, glowing trails that can linger for several minutes after the meteor itself has vanished. These ethereal afterglows are created when meteors ionize the thin air at high altitude, leaving behind a column of glowing gases that slowly fades like cosmic calligraphy written across the sky. Persistent trains are more common during intense meteor showers or when particularly large particles create bright fireballs. They twist and distort in the high-altitude winds, creating ghostly spirals and curves that seem to dance in slow motion. Photographing these trains requires patience and luck, but witnessing them with the naked eye creates an almost mystical experience. The meteor appears, blazes across the heavens, and then leaves behind this fading signature, like a cosmic autograph slowly dissolving into the darkness. These moments remind us that even after the shooting star has ended its brief performance, its presence continues to influence the sky around it. The seasonal progression of meteor showers follows Earth's orbital journey like chapters in an annual story. Each shower has its own character and timing, creating a natural rhythm that connects sky watchers to the planet's movement through space. The year begins with a sharp, brief peak of the quadrantids in early January, often hampered by cold weather but capable of producing spectacular displays for those willing to brave the winter darkness. Spring brings the reliable Lyrids in late April, moderate in intensity but consistent year after year. Summer offers multiple opportunities with the Delta Aquariids in July, leading into the famous Perseids of August, perfect for warm nights and comfortable outdoor viewing. Autumn delivers the swift Orionids in October, remnants of Halley's Comet that streak across the sky with distinctive speed and brightness. The year concludes with December's Geminids, often considered the best shower of the year for their abundance of bright, colorful meteors that seem to hang in the air longer than most. Weather plays a gentle but crucial role in meteor watching, creating natural viewing conditions that can enhance or obscure the celestial display. Clear, dry nights provide the best visibility, allowing even faint meteors to be seen against the star-filled darkness. High humidity can create a subtle haze that dims the fainter shooting stars while leaving the brightest ones still visible. Light clouds moving across the sky create an ever-changing canvas, sometimes blocking meteors and sometimes framing them in wisps of silver. Temperature inversions can create surprisingly stable viewing conditions, with the air so still that meteors appear sharp and well-defined against the motionless sky. Even less than perfect weather can have its charm, with meteors occasionally visible through thin cloud layers, appearing as brief glows rather than distinct streaks. The interplay between earthly weather and cosmic events adds another layer of anticipation to meteor watching, making each viewing session unique and unrepeatable. Urban areas present challenges for meteor watching, but they also offer opportunities for unexpected connections with the cosmos. Light pollution washes out most of the fainter meteors, leaving only the brightest ones visible to city dwellers. However, these bright meteors can be particularly striking against an urban backdrop, appearing suddenly in small patches of dark sky between buildings. Rooftops and urban parks become observing platforms where small groups of people gather to scan the heavens together. The contrast between the busy human world below and the ancient cosmic dance above creates its own form of poetry. Many people experience their first meteor while walking city streets, catching a bright fireball out of the corner of their eye and stopping to wonder what they just witnessed. These urban encounters with meteors often spark a deeper interest in astronomy, leading people to seek out darker skies and fuller experiences of these celestial events. The science behind meteor colors reveals a hidden chemistry lesson written in light across the night sky. Each meteor's brief glow contains information about both the cosmic dust creating it and the atmospheric gases it encounters. Sodium produces a distinctive orange-yellow color, often creating some of the most visible meteor hues. Magnesium burns with a brilliant blue-white light, while iron creates yellow and orange tones. Calcium contributes to the red end of the spectrum, and atmospheric nitrogen can add red hues to a meteor's trail. These colors are often subtle, requiring dark, adapted eyes and careful attention to detect. Long exposure photography can capture and enhance these delicate tints, revealing the full spectrum hidden in each meteor's journey. The realization that each shooting star is essentially a tiny cosmic chemistry experiment, broadcasting the elements it contains through its brief moment of luminescence, adds intellectual wonder to the visual beauty of meteor watching. Temperature differences create their own rhythms in meteor observation throughout the year. Summer meteor showers offer the luxury of comfortable outdoor viewing, with warm nights that invite extended sessions under the stars. Observers can lie on blankets for hours without discomfort, making it easier to spot the subtle meteors that might be missed during brief glimpses. Winter showers present different challenges and rewards, with crystal clear cold air often providing exceptional visibility, but requiring careful preparation for extended outdoor viewing. The contrast between the cold air on your face and the warm layers of clothing creates a heightened awareness of the environment, making each meteor seem more precious and noteworthy. Spring and autumn showers offer moderate conditions with their own seasonal beauty, surrounded by the sounds and scents of changing seasons. The temperature becomes part of the meteor watching experience, influencing not just comfort, but also the quality of observation and the memories formed during these quiet cosmic encounters. Human vision adapts to darkness in ways that enhance meteor watching, creating a natural progression from casual glance to dedicated observation. The eyes take roughly 30 minutes to fully adapt to darkness, gradually revealing fainter stars and improving sensitivity to quick movements across the sky. This adaptation period becomes part of the ritual of meteor watching, a gradual transition from the bright human world to the subtle realm of night vision. Red flashlights help preserve this dark adaptation while allowing observers to check star charts or adjust equipment. As vision improves, meteors that were invisible at first become clearly visible, and the overall richness of the night sky reveals itself layer by layer. This biological process connects meteor watchers to their ancestors who depended on night vision for survival, creating a primal link between modern sky observation and ancient human experiences under the stars. The patience required for proper dark adaptation mirrors the patience needed for meteor watching itself, both requiring a willingness to slow down and let natural processes unfold at their own pace. The predictable nature of meteor showers creates a cosmic calendar that connects modern observers to ancient rhythms of the universe. Each shower arrives with the reliability of seasons, following orbital mechanics that have remained unchanged for millennia. The quadrantids announce the new year with their brief but intense display, while the Eta Aquariids in May bring whispers of Halley's Comet long after the famous visitor has departed. These celestial appointments remind us that we're passengers on a planet following a precise path through space, encountering the same debris trails that our ancestors witnessed centuries ago. There's something deeply reassuring about this cosmic punctuality, knowing that regardless of earthly changes, the meteor showers will continue their appointed rounds with mathematical precision. The universe keeps its own calendar, marking time not in human schedules but in the gentle dance of planets and the scattered remains of ancient comets. Meteor shower photography captures moments that exist for mere seconds, preserving them as lasting memories of cosmic encounters. Long exposure techniques can record meteor trails as brilliant streaks painted across star-filled skies, creating images that often reveal details invisible to the naked eye. Multiple meteors might appear in a single photograph, creating the impression of a celestial fireworks display frozen in time. The process requires patience and preparation, with photographers often spending entire nights under the stars, camera clicking steadily, hoping to capture that perfect moment when a bright meteor crosses their field of view. Many images reveal the subtle colors hidden in meteor trails, the greens and blues and oranges that flash too briefly for eyes to fully appreciate. These photographs become treasured records of nights spent in communion with the cosmos, proof that these fleeting moments of beauty actually occurred in the darkness above our sleeping world. The International Space Station occasionally provides a unique perspective on meteor showers, with astronauts witnessing these cosmic events from above Earth's atmosphere. From their orbital vantage point, meteors appear as brief flashes of light entering the atmosphere below, creating a reverse view of the phenomenon ground-based observers experience. Astronauts have described watching meteors streak beneath them while simultaneously seeing the lights of cities spread across the darkened continents. This perspective shift reminds us that meteors are truly atmospheric phenomena occurring in the thin shell of air that protects our planet. The space station's orbital speed means astronauts see meteors from constantly changing angles, witnessing the same debris streams that create familiar showers, but from viewpoints no human in history could experience until the space age began. Their descriptions add another dimension to our understanding of these cosmic visitors, showing how perspective can transform even the most familiar celestial events into something entirely new. Children often experience their first profound connection to the universe through meteor showers, moments that can spark lifelong interests in astronomy and space exploration. A child's sense of wonder at seeing shooting stars creates memories that often last decades, becoming foundational experiences that shape their relationship with the night sky. Parents and grandparents have passed down the tradition of meteor watching for generations, creating shared experiences under the stars that bond families together through cosmic wonder. School camping trips often time their outdoor adventures to coincide with major meteor showers, giving young people their first taste of the patience and reward that comes with serious sky observation. These early encounters with meteors teach children about the vastness of space, the age of the solar system, and their place in the cosmic story. The simplicity of lying on a blanket and watching shooting stars makes astronomy accessible to young minds, requiring no equipment or technical knowledge, just curiosity and a willingness to look up into the darkness. Radio meteors provide a completely different way to experience these cosmic events, allowing observers to detect meteors even during daylight hours or cloudy weather. When meteors enter the atmosphere, they create ionized trails that briefly reflect radio waves, creating distinctive pings and whistles that can be heard through specialized equipment. Radio enthusiasts tune into specific frequencies to monitor meteor activity, creating an auditory landscape of cosmic events that most people never know exists. This invisible dimension of meteor showers reveals that these events affect more than just the visual spectrum, influencing radio communications and creating electromagnetic signatures that persist longer than the visible trails. The radio reflection technique has allowed scientists to study meteor showers continuously, building detailed databases of activity levels and timing that supplement visual observations. For those who cannot easily observe meteors visually due to urban light pollution or physical limitations, radio detection offers an alternative pathway to experience these cosmic events through sound rather than sight. The dust trails that create meteor showers gradually evolve and change over thousands of years, creating subtle variations in the annual displays that careful observers can detect over decades of watching. Fresh debris from recent comet passages creates dense, intense meteor activity, while older trails spread out and become more diffuse, producing gentler but longer-lasting showers. Gravitational influences from planets gradually reshape these debris streams, sometimes concentrating particles for spectacular outbursts, and sometimes dispersing them until showers fade into cosmic background noise. The Leonids demonstrate this evolution dramatically, producing modest annual displays most years, but erupting into spectacular meteor storms every 33 years when Earth encounters the densest part of the debris trail left by Comet Tempel-Tuttle. These variations remind us that meteor showers are not static phenomena, but dynamic, evolving systems that change on timescales both longer and shorter than human lifespans. Each year's display is subtly different from the last, making every meteor shower observation unique, while maintaining the overall patterns that make these events predictable and reliable. Atmospheric conditions at meteor altitudes create their own weather patterns that influence how meteors appear from the ground. High-altitude winds can bend and distort meteor trails, creating curved paths instead of straight lines. Temperature variations in the mesosphere can affect how completely meteors vaporize, sometimes allowing larger particles to penetrate deeper into the atmosphere before burning up. Seasonal changes in atmospheric density alter the brightness and duration of meteor trails, with summer's expanded atmosphere creating longer, more visible displays than winter's compressed air layers. These subtle influences mean that identical particles entering Earth's atmosphere at different times of year can create markedly different visual effects. Understanding these atmospheric variables adds another layer of appreciation for meteor watching, recognizing that the beautiful displays we see result from complex interactions between cosmic debris and our planet's protective envelope of air. Meteor watching has evolved into a citizen science opportunity, with amateur observers contributing valuable data to professional research projects. Organizations coordinate global observation campaigns during major meteor showers, collecting timing and brightness data from hundreds of volunteers around the world. These collective observations help scientists understand the structure and evolution of debris streams with greater precision than any single observatory could achieve. Modern smartphone apps allow observers to record meteor sightings with timestamps and location data, creating vast databases of activity that reveal subtle patterns in shower behavior. The democratization of meteor science means that anyone with clear skies and patience can contribute to our understanding of these cosmic events. This collaboration between amateur and professional astronomers continues a tradition stretching back centuries, when careful observers recording what they saw in the night sky formed the foundation of modern meteor science. The silence that accompanies meteor watching creates space for reflection and introspection that few other activities provide. In our noisy modern world, lying quietly under the stars creates a rare opportunity for uninterrupted thought and peaceful contemplation. The gentle anticipation of waiting for meteors encourages a meditative state where the mind can wander freely while remaining alert for sudden movements across the sky. Many observers find that their most creative thoughts and clearest insights come during these quiet hours under the stars, when the usual distractions of daily life fade away. The rhythm of meteor watching, periods of patient waiting punctuated by moments of excitement when shooting stars appear, mirrors natural cycles of rest and activity that our busy lives often disrupt. This force reminding us that not slowness becomes therapeutic. Everything worthwhile can be rushed or scheduled, that some experiences require us to simply be present and receptive to whatever the universe chooses to offer. Weather fronts and atmospheric disturbances can create unexpected enhancements to meteor displays, with some of the most memorable observations occurring during unusual atmospheric conditions. Temperature inversions can create superstable air that makes meteors appear unusually sharp and well-defined against the stars. High-pressure systems often bring the crystal-clear skies that reveal even the faintest shooting stars, while the approach of weather fronts can create atmospheric lensing effects that briefly intensify meteor brightness. Observers have reported seeing meteors that seem to pulsate or change color as they traveled through layers of air with different temperatures and densities. These atmospheric interactions remind us that meteor watching occurs at the intersection of cosmos, icy and terrestrial influences, where space-traveling dust meets Earth's ever-changing envelope of air. The unpredictability of these atmospheric enhancements adds an element of surprise to meteor watching, ensuring that even familiar annual showers can occasionally provide unexpected moments of extraordinary beauty that remain vivid in memory for years afterward. The mathematics of meteor shower prediction reveals the elegant precision hidden within apparent cosmic chaos. Astronomers can calculate exactly when Earth will encounter specific debris streams, often predicting peak activity times to within hours, years in advance. These calculations involve tracking the orbital mechanics of both Earth and the parent comet, accounting for gravitational influences from planets and the gradual dispersal of particles over time. The precision required rivals that of spacecraft navigation, with tiny variations in timing or trajectory, capable of shifting shower peaks by hours or even days. Computer models now simulate the evolution of debris streams over thousands of years, revealing how ancient comet passages continue to influence modern meteor displays. This mathematical foundation transforms meteor watching from simple sky gazing into participation in a cosmic clockwork that has been ticking with astronomical precision since the solar system formed billions of years ago. Professional meteor research has revealed that some particles creating these gentle light shows are older than Earth itself. Isotopic analysis of recovered meteorites suggests that certain debris streams contain materials that predate the formation of our planet. Pristine samples from the earliest days of solar system formation. These ancient grains carry within them the chemical signatures of stellar processes that occurred before our sun was born, making each meteor a messenger from deep cosmic time. When you watch a shooting star, you might be seeing the final moment of a particle that has traveled through space for over 4.5 billion years, unchanged since the primordial disk of dust and gas that would become our solar system first began to coalesce. This temporal perspective adds profound depth to meteor watching, connecting each brief streak of light to the vast sweep of cosmic history that led to this moment under these particular stars. Meteor showers influence more than just visual astronomy, creating subtle effects that ripple through Earth's upper atmosphere and beyond. The ionization trails left by meteors can briefly disrupt radio communications, creating momentary blackouts or unusual signal propagation that radio operators have learned to recognize. These same ionized columns can reflect radio waves in unexpected ways, sometimes allowing distant stations to be heard clearly for a few seconds before the trail dissipates. Satellite operators track major meteor showers because the increased atmospheric activity can affect orbital calculations and communication links. Even GPS systems can experience minor disruptions during intense meteor activity, as the ionized trails interfere with the precise timing signals that enable global positioning. These technological connections remind us that meteor showers are not just beautiful displays, but active phenomena that interact with our modern electronic world in subtle but measurable ways. The evolution of meteor shower observing reflects humanity's changing relationship with darkness and the night sky. A century ago, most people lived in rural areas where meteor showers were easily visible from their own backyards, creating shared community experiences as neighbors gathered to watch major displays together. The gradual spread of electric lighting and urban development has transformed meteor watching into a specialized activity that often requires travel to dark sky locations. This change has created a new form of astronomical pilgrimage, with dedicated observers driving for hours to escape city lights and experience meteor showers as they were meant to be seen. Dark sky preserves and astronomy parks have become sanctuaries, where the ancient human experience of meteor watching can still unfold naturally. Places where the night sky remains connected to its cosmic context, rather than being overwhelmed by artificial illumination. Cultural interpretations of meteor showers have evolved alongside human understanding of their true nature, but the sense of wonder they inspire remains remarkably consistent across time and cultures. Ancient Chinese astronomers called meteors guest stars and carefully recorded their appearances in imperial chronicles that modern researchers still consult today. Indigenous peoples of North America developed rich mythologies around meteor showers, often that connected the earth, seeing them as spiritual events whirled to celestial realms. European medieval chronicles describe meteor displays as omens and portents, reflecting a worldview where cosmic events held direct meaning for human affairs. Modern scientific understanding has replaced supernatural interpretations with knowledge of orbital mechanics and cosmic debris. Yet the fundamental human response of awe and contemplation remains unchanged. We still gather under the stars to watch meteors with the same sense of participation in something larger than ourselves. Technological advances have revolutionized how we detect and study meteors, while somehow making the basic experience of watching them even more magical. Automated cameras now monitor the entire sky continuously, capturing meteors too faint for human eyes and tracking their precise paths through the atmosphere. Radar systems detect meteors during daylight hours and cloudy weather, revealing shower activity that would otherwise go unnoticed. Spectroscopic analysis of meteor light can determine the exact chemical composition of particles that existed for mere seconds as visible phenomena. Yet all this technology serves to enhance rather than replace the simple pleasure of lying under the stars and watching shooting stars with naked eyes. The instruments reveal the science behind the beauty, but they cannot replicate the personal experience of witnessing these cosmic visitors in their natural setting of star-filled darkness. Meteor shower seasonality connects to broader patterns of life on Earth in ways that feel almost intentional in their timing. Summer showers like the Perseids arrive when warm weather makes comfortable outdoor viewing possible, inviting families and communities to share the experience together. Winter displays test the dedication of serious observers while rewarding them with some of the most spectacular shows of the year, visible through crystal clear cold air that enhances even faint meteors. Spring showers mark renewal and awakening, arriving as life returns to northern landscapes and daylight hours begin to lengthen. Autumn meteors accompany the season of harvest and reflection, providing contemplative moments as the year winds toward its close. This natural calendar creates a rhythm that connects human seasonal experiences to the cosmic clockwork of orbital mechanics, making meteor showers feel like they belong to the natural cycles that govern life on Earth. The debris that creates meteor showers represents the solar system's ongoing process of change and renewal, a cosmic recycling program that had been operating for billions of years. Comets gradually shed their substance with each passage near the sun, scattering particles that eventually find their way to Earth as gentle shooting stars. This process slowly transforms solid comet nuclei into dispersed streams of cosmic dust, distributing materials throughout the solar system in patterns that will persist for millions of years. The particles themselves undergo their own transformation, changing from frozen comet fragments to luminous atmospheric phenomena, and finally to microscopic dust that settles slowly toward Earth's surface. Some scientists estimate that several tons of cosmic material reaches Earth every day, most of it arriving as invisible micrometeorites too small to create visible trails. This constant gentle rain of space dust represents the solar system's way of sharing materials between its various components. Individual meteors within a shower can tell remarkably different stories despite originating from the same parent comet, revealing the complex history hidden within seemingly uniform debris streams. Some particles are dense and metallic, creating bright flashes that seem to explode across the sky before vanishing completely. Others are fluffy and fragile, producing long, slow trains that drift across the heavens like cosmic dandelion seeds. The variation reflects different parts of the parent comet's composition, from its rocky core to its outer layers of volatile ices and organic compounds. Particles that separated from the comet during different orbital passages can have slightly different trajectories, creating variations in speed and angle that make each meteor unique even within the same shower. These individual differences remind us that every shooting star represents a specific piece of cosmic history, a particular fragment with its own journey through space and time. Atmospheric entry creates a brief but intense drama as cosmic particles encounter Earth's protective envelope, with explosive results that transform space dust into earthly light. The initial contact occurs at altitudes where the air is so thin it barely qualifies as atmosphere at all. Yet even this tenuous gas is sufficient to begin the heating process that will consume the meteor. The particle compresses the air in front of it like a tiny supersonic aircraft, creating temperatures that can exceed those found on the surface of the sun. This extreme heating vaporizes not only the meteor, but also the surrounding air, creating a column of glowing plasma that extends for miles behind the original particle. The entire process typically lasts only a few seconds, but in that brief time, a grain of cosmic dust creates a light show visible from hundreds of miles away, demonstrating the tremendous energies involved in even the gentlest celestial phenomena. Photography has transformed meteor watching from a purely observational activity into a creative art form that captures and shares the beauty of these cosmic events with people who might never experience them directly. Digital cameras can record meteors too faint for human vision, revealing the full extent of shower activity that occurs beyond the threshold of naked eye observation. Time-lapse photography compresses hours of meteor activity into minutes of viewing, creating composite images that show the radiant point and the full geometry of debris stream encounters. Modern image processing techniques can enhance the subtle colors hidden in meteor trails, revealing the chemical signatures that flash too briefly for eyes to appreciate. Social media has created global communities of Meteor photographers who share their captures in real time during major showers, allowing people around the world to experience the same cosmic events from different perspectives and locations. The study of meteor shower variations over decades has revealed subtle patterns that reflect the dynamic nature of debris streams and their interaction with planetary gravitational fields. Some showers show gradual increases or decreases in activity over periods of years, indicating changes in the density or distribution of particles along their orbital paths. Others display sudden outbursts when Earth encounters particularly dense clumps of debris, creating unexpected meteor storms that can produce thousands of shooting stars per hour. Long-term records kept by dedicated observers have become valuable scientific data sets that help researchers understand how debris streams evolve over timescales longer than individual human lifespans. These variations add an element of unpredictability to meteor watching that keeps even experienced observers alert for unexpected developments during supposedly routine annual displays. The connection between meteor showers and their parent comets creates a form of cosmic archaeology that allows scientists to study objects that may no longer be visible or accessible to direct observation. Some meteor showers continue to appear annually, even though their parent comets have not been seen for centuries, having either disintegrated completely or moved to orbital positions where they no longer approach the inner solar system. The debris streams become fossil records of these vanished comets, preserving information about their composition and structure long after the original objects have disappeared. Analysis of meteor shower characteristics can reveal details about comet nuclei that are impossible to obtain through telescopic observation alone, including the distribution of dE, different materials within the original body, and the processes that occurred during its active phases near the Sun. Advanced radar techniques have opened an entirely new window into meteor shower research, allowing continuous monitoring of cosmic debris regardless of weather, daylight, or atmospheric conditions that limit optical observations. These systems can detect meteors too small and faint to produce visible trails, revealing the full population of particles entering Earth's atmosphere during shower periods. Radar observations have shown that visual meteor counts represent only a small fraction of the total activity occurring during major showers, with thousands of invisible micrometeors accompanying each visible shooting star. The radar data also provides precise measurements of meteor velocities and trajectories, allowing researchers to trace particles back to their origins in space with greater accuracy than optical observations alone can achieve. This technology has revealed that meteor shower activity occurs continuously throughout the year, not just during the well-known annual peaks that attract public attention. The psychological effects of meteor watching extend beyond simple entertainment, creating experiences that can shift perspective and inspire long-term changes in how people view their place in the universe. Many observers describe meteor showers as humbling experiences that put daily concerns into cosmic context, providing natural therapy through connection with something vast and enduring. The patience required for meteor watching teaches a form of mindfulness that can be difficult to achieve in our hurried modern world, encouraging present moment awareness and acceptance of natural rhythms beyond human control. Children who experience meteor showers often develop lasting interests in science and space exploration, with many professional astronomers tracing their career origins to childhood memories of watching shooting stars. The shared experience of meteor watching can strengthen family bonds and friendships, creating memories associated with wonder and discovery rather than material consumption or technological entertainment. Seasonal variations in Earth's atmosphere create subtle but noticeable differences in how meteors appear throughout the year, with each season offering its own characteristic viewing conditions and atmospheric effects. Summer's warm, expanded atmosphere can create longer, more visible meteor trails, as particles encounter denser air at higher altitudes than during winter months. The increased atmospheric turbulence of summer can also cause meteors to appear to flicker or pulse as they pass through layers of air with different temperatures and densities. Winter's cold, compressed atmosphere often provides exceptionally clear viewing conditions, but can make meteors appear brighter and more brief as particles encounter the denser air layers more suddenly. Spring and autumn offer moderate conditions with their own seasonal characteristics, including the temperature inversions and atmospheric stability that can create ideal viewing conditions for patient observers willing to adapt to changing weather patterns. The global nature of meteor shower observation creates opportunities for international collaboration and shared experiences that transcend political and cultural boundaries, uniting people around the world in appreciation of cosmic phenomena that belong to no single nation or culture. Observers in different time zones can track the same meteor shower as Earth's rotation carries the radiant point across the sky, creating a continuous global observation that follows the planet's spin. Online communities share real-time reports and images during major showers, allowing people to experience meteor displays from multiple perspectives and geographic locations simultaneously. This global sharing has created informal networks of amateur astronomers who coordinate observations and contribute to scientific understanding through their collective efforts. The universal human response to meteor showers demonstrates how natural phenomena can create common ground and shared wonder that bridges differences in language, culture, and nationality. The debris streams that create meteor showers exist in a state of constant, gentle motion, slowly spreading and evolving as they orbit the sun in patterns that stretch across millions of miles of space. These cosmic rivers of dust follow elliptical paths that can take decades or centuries to complete, gradually widening and dispersing as gravitational forces from planets tug at individual particles. The process creates variations in meteor shower intensity that unfold over human lifetimes, with some years producing abundant displays and others offering more modest celestial performances. Observers who watch the same meteor shower for decades often notice these subtle changes, becoming witnesses to the slow-motion evolution, streams of debris forming when comets pass through the inner solar, our system generations ago. The particles continue their ancient journeys, some eventually spiraling into the sun, while others drift toward the outer reaches of the solar system. But for a brief period in their cosmic wandering, they intersect with Earth's path to create moments of gentle beauty in our night skies. The temperature extremes experienced by meteor particles during their brief atmospheric journey create conditions more intense than almost anything found naturally on Earth's surface. Within seconds, cosmic dust traveling at tens of thousands of miles per hour encounters increasing atmospheric resistance that generates temperatures exceeding 10,000 degrees Fahrenheit. These extreme conditions vaporize not only the meteor itself, but also create a column of superheated air that glows with the same physics that powers stars. The process is so efficient that particles the size of rice grains can create brilliant fireballs visible across multiple states, while dust specks smaller than sand grains produce the gentle streaks that make up the majority of meteor shower displays. This transformation from solid matter to luminous gas represents one of nature's most efficient energy conversions, turning the kinetic energy of orbital motion into brief moments of atmospheric light that can be seen from hundreds of miles away. Timing variations in meteor shower peaks reflect the complex gravitational dance between Earth, the debris streams, and the massive planets of our solar system. Jupiter's immense gravitational field can subtly shift the timing of meteor encounters by hours or even days, while the combined influence of all the planets creates variations that unfold over decades and centuries. These gravitational perturbations mean that meteor shower predictions must account for the positions and movements of multiple celestial bodies, making accurate forecasting a sophisticated exercise in celestial mechanics. Some years, Earth encounters debris streams earlier or later than average, creating unexpected variations in timing that keep even experienced observers alert for surprises. The precision required to predict these variations demonstrates the interconnected nature of solar system dynamics, where the motion of every significant body influences the paths of countless tiny particles scattered throughout interplanetary space. Amateur meteor observers have contributed to scientific understanding in ways that professional researchers could never achieve alone, creating vast databases of observations that span continents and decades. Individual observers recording the timing, brightness, and color of meteors they see contribute to a collective understanding of debris stream structure and evolution that no single observatory could match. The geographic distribution of amateur observers allows for tracking meteor showers as they become visible across Earth's rotation, creating continuous coverage that reveals details about shower duration and intensity variations. Many significant meteor discoveries have come from dedicated amateurs who noticed unusual activity or unexpected shower behavior during their regular observing sessions. This collaboration between professional and amateur astronomers continues a tradition that stretches back to the earliest days of meteor research, when careful visual observations form the foundation of our understanding of these cosmic phenomena. The optical physics of meteor trails involves the same principles that create neon signs and aurora displays, with excited atoms and molecules releasing photons as they return to lower energy states after being heated by the meteor's passage. Different elements produce characteristic colors when heated to extreme temperatures, creating a spectroscopic signature that reveals the chemical composition of both the meteor and the atmospheric gases it encounters. Sodium creates distinctive orange-yellow emissions, while magnesium produces blue-white light that can be visible even through moderate light pollution. Iron contributes yellow and orange hues, and atmospheric nitrogen adds red tones to meteor trails. These colors often appear too briefly and faintly for casual observation, but careful observers with dark adapted eyes can sometimes detect the subtle tints that reveal the hidden chemistry occurring dozens of miles overhead. Long exposure photography can capture and enhance these delicate colors, preserving evidence of the cosmic chemistry experiments that unfold during each meteor's brief moment of visible existence. Radio detection of meteors has revealed a hidden dimension of these cosmic events that extends far beyond what visual observation alone can capture. When meteors create ionization trails in the upper atmosphere, these columns of charged particles can reflect radio waves in ways that create distinctive audio signatures, audible through specialized equipment. Radio meteor detection works around the clock and in all weather conditions, allowing continuous monitoring of shower activity that supplements and extends visual observations. The technique has shown that meteor activity continues at significant levels even during daylight hours and cloudy periods when optical observation is impossible. Some radio enthusiasts have developed sophisticated systems that can automatically count and analyze meteor echoes, creating detailed records of shower activity that span years of continuous data collection. This radio dimension of meteor research demonstrates how the same cosmic events that create visual beauty also influence the electromagnetic environment around our planet in subtle but measurable ways. Meteor shower debris represents samples from some of the most remote and ancient regions of the solar system, places so distant and cold that materials have remained virtually unchanged since the earliest days of planetary formation. Comets that create meteor showers often originate in the Kuiper Belt, or even the distant Oort cloud, regions where temperatures are so low that volatile compounds remain frozen for billions of years. When these ancient wanderers approach the sun and begin shedding material, they release particles that carry chemical signatures from the solar system's youth. Some meteor shower particles may contain organic compounds that formed in interstellar space before our solar system even existed, making each shooting star a potential messenger from cosmic environments we can barely imagine. The study of meteor shower composition therefore provides insights into conditions that existed during the solar system's formation, offering glimpses into a primordial era when planets were still forming from the collision and accretion of countless smaller bodies. The meditative aspects of meteor watching create natural opportunities for contemplation and reflection that few other activities in our modern world can match. The patient waiting required for meteor observation encourages a state of relaxed alertness that many people find deeply calming and restorative. Unlike many forms of entertainment that demand constant attention and stimulation, meteor watching rewards quiet patience with unexpected moments of wonder that arrive on their own schedule. The silence and darkness required for optimal viewing create natural barriers to the distractions and anxieties of daily life, allowing the mind to settle into rhythms that feel more connected to natural cycles than human schedules. Many observers find that their most creative insights and peaceful moments come during these quiet hours under the stars, when the usual mental chatter fades away and deeper awareness can emerge. The unpredictable timing of meteors maintains just enough engagement to prevent boredom, while allowing space for the kind of unfocused attention that can be profoundly refreshing in our overstimulated world. Atmospheric density variations create subtle but noticeable effects on meteor appearance that change throughout the night as Earth rotates and atmospheric conditions shift. The pre-dawn hours often provide the most stable viewing conditions as temperature differences between ground and upper atmosphere minimize the turbulence that can make meteors appear to flicker or dance across the sky. High-pressure weather systems typically create the crystal-clear conditions that allow even faint meteors to be visible, while approaching weather fronts can create atmospheric lensing effects that temporarily enhance meteor brightness before clouds arrive. Temperature inversions can create remarkably stable air columns that make meteors appear unusually sharp and well-defined against the star background. These atmospheric variables remind observers that meteor watching occurs at the intersection of cosmic and terrestrial influences, where space-traveling particles meet Earth's ever-changing envelope of protective gases. Understanding these conditions can help observers choose optimal times and locations for meteor watching, while adding another layer of appreciation for the complex interactions that create these beautiful displays. Children's responses to meteor showers often capture the pure wonder and excitement that can become dulled by adult familiarity with scientific explanations. Young observers typically react to meteors with spontaneous delight and amazement that reminds adults of their own capacity for cosmic wonder. The simple act of lying on a blanket and watching shooting stars with children can reawaken appreciation for phenomena that might otherwise be taken for granted. Many families create traditions around major meteor showers, with annual camping trips or backyard viewing sessions that become cherished memories, connecting generations through shared experiences of cosmic beauty. These early exposures to meteor showers often plant seeds of scientific curiosity that can grow into lifelong interests in astronomy and space exploration. The accessibility of meteor watching, requiring no equipment or technical knowledge beyond patience and clear skies, makes it an ideal introduction to astronomy for young minds ready to discover their connection to the wider universe. Professional meteor research has revealed that some particles creating shooting stars may have traveled through interstellar space for millions of years before joining our solar system, carrying within them chemical signatures from stellar processes that occurred before our sun was born. These interstellar visitors mixed with native solar system materials during the chaotic early period, when planets were forming from the collision and merger of countless smaller bodies. Isotopic analysis of recovered meteorites has identified grains that definitely formed in other star systems, suggesting that some meteor shower particles may represent samples of truly alien matter that has found its way into our cosmic neighborhood. When observers watch meteors during major showers, they may be witnessing the final moments of particles that began their journey in the atmospheres of distant stars, traveled through the galaxy for eons, and finally encountered our solar system's gravitational influence. This cosmic perspective transforms each shooting star from a simple atmospheric phenomenon into a messenger carrying information about stellar processes and galactic evolution that occurred long before Earth existed. The electromagnetic effects of meteor trails extend beyond simple ionization, creating temporary modifications to Earth's upper atmosphere that can influence radio propagation and satellite communications in subtle but measurable ways. Dense meteor showers can create sufficient ionization to affect the reflection and transmission of radio waves, sometimes allowing distant radio stations to be heard clearly for brief periods. These same ionization effects can influence GPS satellite signals, creating momentary variations in positioning accuracy during periods of intense meteor activity. Military and commercial communication systems that rely on precise radio timing have learned to account for meteor shower effects in their operational planning. Research satellites equipped with sensitive instruments can detect the electromagnetic signatures of meteors too small to be visible from the ground, revealing the full extent of cosmic debris entering Earth's atmosphere. These technological connections demonstrate that meteor showers are not merely visual spectacles, but active phenomena that interact with our modern electronic infrastructure in ways that would have seemed impossible to earlier generations of sky watchers. Urban meteor watching has evolved into its own specialized form of astronomy as city dwellers adapt to challenging conditions created by artificial lighting and atmospheric pollution. Dedicated urban observers learn to identify the small patches of darker sky between buildings where meteors might be visible, often discovering viewing opportunities that less experienced observers would overlook. Rooftops, urban parks, and even busy streets can occasionally provide glimpses of the brightest meteors, creating unexpected moments of cosmic connection in the midst of human-built environments. Light pollution filters out the faintest meteors, but can actually enhance the visibility of bright fireballs by providing contrast that makes them stand out dramatically against the artificially illuminated sky. Many people experience their first meteor while walking city streets or sitting in urban parks, catching a brilliant shooting star out of the corner of their eye and stopping to wonder they just witnessed what. These urban encounters often motivate people to seek out darker skies and fuller experiences of meteor showers, beginning journeys that lead from casual city to dedicate observations, dark sky pilgrimages. The seasonal rhythm of meteor showers creates a natural calendar that connects modern observers to ancient cycles of cosmic time, with each major shower arriving with the reliability of celestial clockwork. This predictable progression through the year provides structuration for and anticipates sky dedicate watchers who plan their observe of cosmic duels around the display's annualing sequence. The Drantids mark the beginning of each year's meteor calendar with their brief but intense early January peak, followed by the steady spring arrival of the Lyrids in April. Summer brings multiple opportunities with the reliable Perseids highlighting August nights, while autumn delivers the swift Orionids and unpredictable Leonids. The year concludes with December's abundant Geminids, often providing the most spectacular displays of the entire annual cycle. This natural progression creates a rhythm that feels both ancient and eternal, connecting contemporary observers to the same cosmic events that have marked the passage of seasons for thousands of human generations. Scientific analysis of meteor shower variations has revealed complex relationships between debris stream evolution and the gravitational influences of major planets, creating a dynamic system where shower characteristics change gradually over periods of decades and centuries. Computer models can now simulate the evolution of debris streams over thousands of years, showing how particles gradually spread along orbital paths while maintaining the basic structure that creates recognizable annual showers. Some streams show evidence of periodic compression and dispersion as they interact with planetary gravity fields, creating cycles of enhanced and diminished activity that unfold over timescales longer than individual human observation periods. The Leonid meteors demonstrate this evolution dramatically, producing spectacular meteor storms approximately every 33 years, when Earth encounters the densest concentrations of particles in the debris stream. These long-term patterns remind observers that each year's meteor shower represents a single snapshot in an ongoing process of cosmic evolution that connects the present moment to both the ancient past and the distant future of our solar system. The acoustic silence of meteor showers creates one of the most distinctive aspects of these cosmic displays, offering visual spectacle accompanied by the natural sounds of night rather than any noise from the meteors themselves. This silence isn't merely absence of sound, but represents the vast distances involved in meteor phenomena, with the light shows occurring dozens of miles above the reach of Earth's sound-conducting atmosphere. The quiet creates space for other sensory experiences during meteor watching, from the rustle of leaves in evening breezes to the distant calls of nocturnal birds, or the gentle sounds of breathing and heartbeats that become noticeable in the stillness. Many observers find this combination of visual excitement and auditory calm deeply relaxing, creating a form of natural meditation where attention alternates between focused sky scanning and broader awareness of the peaceful nighttime environment. The silence also enhances the social aspects of group meteor watching, allowing quiet conversation and shared reactions to bright meteors without competing with artificial noise or electronic distractions. Photographic techniques have evolved to capture not just individual meteors, but the overall patterns and geometries of entire shower displays, creating artistic interpretations that reveal the mathematical beauty hidden within these cosmic events. Long exposure photography can record multiple meteors in single images, showing how shooting stars radiate outward from their apparent source points among the constellations. Time-lapse techniques compress hours of meteor activity into minutes of viewing, revealing the full scope and rhythm of shower displays that would be impossible to appreciate through real-time observation alone. Digital processing can enhance the subtle colors and details in meteor trails, bringing out information that exists below the threshold of human vision. Some photographers create composite images that combine dozens of individual meteor captures into single artworks that show the full geometry and beauty of major showers. These photographic interpretations have become art forms in their own right, while also contributing to scientific understanding of meteor shower structure and behavior. The global community of meteor observers has created informal networks that span continents and time zones, allowing real-time sharing of observations and creating collective experiences that transcend geographic boundaries. Social media platforms enable observers to share images and reports instantly during major showers, creating virtual viewing parties where people around the world can experience the same cosmic events from different perspectives. This global connectivity has revealed regional variations in meteor shower visibility and intensity that individual observers might never notice on their own. International meteor observation campaigns coordinate efforts across multiple countries and continents, creating data sets that reveal details about debris stream structure and evolution. The shared human experience of meteor watching creates common ground that bridges differences in culture, language, and nationality, demonstrating how natural phenomena can unite people in appreciation of cosmic beauty that belongs to no single nation or group. Technological advances in meteor detection have revealed that visible shooting stars represent only a small fraction of the total cosmic material entering Earth's atmosphere during shower periods, with thousands of invisible micrometeors accompanying each observable trail. Radar systems can detect particles too small to create visible light, showing that meteor shower activity occurs continuously at levels far exceeding what optical observation alone can reveal. Automated camera networks now monitor the entire sky continuously, capturing meteors too faint for human observers while providing precise measurements of brightness, color, and trajectory. Spectrographic analysis of meteor light can determine the exact elemental composition of particles in real time, revealing the chemistry of cosmic dust as it transforms into luminous plasma. These technological capabilities have transformed meteor shower research from a largely observational science into a quantitative field capable of detailed analysis and prediction. Yet somehow, the fundamental experience of watching shooting stars with naked eyes remains as magical and meaningful as ever. Human vision adapts to meteor watching in ways that create a natural progression from casual sky glancing to dedicated cosmic observation, with physiological changes that enhance sensitivity to quick movements and faint lights. The process of dark adaptation takes roughly 30 minutes to complete, gradually revealing fainter stars and improving the eye's ability to detect subtle meteor trails that would be invisible under normal lighting conditions. This adaptation period becomes part of the ritual of serious meteor watching, creating a natural transition from the bright human-made world to the subtle realm of night vision. Peripheral vision becomes particularly important during meteor observation, as the edges of the visual field are more sensitive to motion than the central focus area, where most people instinctively look for meteors. Learning to use relaxed, unfocused vision while scanning the sky can dramatically increase the number of meteors detected during any given observing session. This visual training connects modern observers to ancient human skills that were once essential for survival, creating a primal link between contemporary sky watching and the night vision capabilities that helped our ancestors navigate and hunt in darkness. The debris creating meteor showers continues its cosmic journey long after producing earthly light shows, with particles following complex trajectories that can eventually carry them throughout the solar system or beyond. Some meteoric dust settles slowly through Earth's atmosphere over periods of weeks or months, eventually reaching the surface as micrometeorites too small to be noticed individually, but significant in total mass. Other particles retain enough velocity after atmospheric encounter to continue into space, potentially carrying terrestrial atmospheric gases to other parts of the solar system. The largest fragments that survive atmospheric entry as meteorites become permanent additions to Earth's mass, carrying within them chemical information about their cosmic origins and the extreme conditions they experience during atmospheric passage. This ongoing exchange of material between Earth and space represents part of the solar system's natural recycling process, where matter continuously moves between planets, moons, asteroids, and comets in patterns that have been operating for billions of years. Individual meteors within major showers can display remarkably different characteristics, despite originating from the same parent comet, revealing the complex internal structure and composition variations within the original celestial body. Some particles create brief, intensely bright flashes that seem to explode across the sky before vanishing completely, while others produce long, slow trains that drift gracefully through the upper atmosphere like cosmic silk scarves. The variations reflect different densities, compositions, and sizes within the debris stream, with some particles consisting primarily of rocky material, while others contain more volatile ices and organic compounds. Entry angles and velocities also vary slightly among particles in the same shower, creating differences in how completely meteors vaporize and how long their trails remain visible. These individual characteristics remind observers that every shooting star represents a unique piece of cosmic history with its own particular, a specific fragment journey through space and time that culminates in a moment of atmospheric interaction, brief but beautiful. The study of ancient meteor shower records has revealed that some cosmic displays have been visible to human observers for thousands of years, creating an unbroken chain of shared experience that connects contemporary skywatchers to countless previous generations. Chinese imperial astronomers kept detailed records of meteor showers for over 2 millennia, documenting variations researchers still cons in intensity and timing that modern ult when studying long-term debris stream evolution. European medieval chronicles describe spectacular meteor displays in language that captures both the wonder and occasional fear these events inspired in pre-scientific cultures. Native American oral traditions preserve memories of exceptional meteor showers that occurred centuries before written records began, demonstrating the lasting impression these cosmic events made on human consciousness. These historical connections remind modern observers that they are participating in one of humanity's oldest shared experiences, looking up at the same stars and witnessing the same cosmic processes that have inspired wonder and contemplation throughout recorded history. Atmospheric chemistry at meteor altitudes creates unique conditions where cosmic particles encounter an environment unlike anything found at Earth's surface, leading to chemical reactions and energy exchanges that occur nowhere else in our immediate cosmic neighborhood. The extreme thinness of air at meteor altitudes means that individual atoms and molecules can travel significant distances before colliding with other particles, creating conditions more similar to laboratory vacuum chambers than to the dense atmosphere we experience on the ground. When high-velocity cosmic dust encounters this tenuous environment, it creates temporary regions of extremely high temperature and pressure that can trigger chemical reactions impossible under normal terrestrial conditions. Some of these reactions may create exotic compounds that exist only briefly before dispersing into the surrounding atmosphere, making meteor trails temporary laboratories for exotic chemistry experiments. The study of these high-altitude chemical processes provides insights into conditions that may exist in other planetary atmospheres or in interstellar space. Using meteor trails as natural experiments in extreme chemistry that would be impossible to replicate artificially. The physics of meteor trail formation involves processes so precise they seem almost choreographed by the universe itself. As cosmic particles compress the thin air ahead of them, They create shock waves that propagate outward in perfect spherical patterns, disturbing atmospheric molecules in mathematically predictable ways. The column of heated air behind each meteor follows fluid dynamics equations that govern everything from water flowing around a stone to air moving over aircraft wings. These invisible shock waves can sometimes be detected by sensitive instruments on the ground, revealing that meteors create more than just light. They generate pressure waves that ripple through the upper atmosphere like cosmic thunder too high and faint for human ears to perceive. The energy released during this process follows conservation laws that connect each tiny meteor to the fundamental physics governing stars, planets, and galaxies. Understanding these mechanisms transforms meteor watching from simple sky gazing into witnessing demonstrations of universal physical principles playing out in real time dozens of miles overhead. Temperature gradients in the mesosphere create invisible layers that can dramatically affect how meteors appear, with some particles seeming to flicker or pulse as they pass through regions of varying air density and composition. These atmospheric layers shift and flow like invisible ocean currents, sometimes concentrating or dispersing the gases that meteors encounter during their brief journey toward Earth. Seasonal changes in upper atmospheric temperature can alter the altitude at which meteors first become visible, making summer displays appear different from winter showers, even when identical particles are involved. The interaction between meteoric heating and these temperature layers can create unusual visual effects, with some meteors appearing to brighten suddenly as they enter war, mere air masses, or dimming as they pass through cooler regions. Solar activity can influence these atmospheric conditions, creating subtle connections between meteor shower appearance and the 11-year solar cycle that governs space weather throughout the inner solar system. Professional meteor networks have revealed that the cosmic dust arriving during major showers carries isotopic signatures that provide direct evidence of stellar nucleosynthesis processes that occurred in distant stars billions of years ago. Some particles contain ratios of elements that could only have formed in the cores of massive stars during their final moments before going supernova, making each meteor shower a delivery of stellar archaeology. These exotic isotopes mixed with ordinary solar system materials during the chaotic period when planets were forming, creating debris streams that sample both local and galactic chemical processes. When scientists analyze the light spectra from bright meteors, they can sometimes detect these stellar fingerprints in real time, watching ancient starlight manifest as fleeting atmospheric chemistry. The realization that meteor showers bring samples of other stars directly to our planet adds profound depth to the experience of watching shooting stars. Knowing that some of the light we see represents matter forged in stellar furnaces that burned out long before our solar system existed. Radio astronomy techniques applied to meteor research have discovered that some cosmic particles create electromagnetic signatures that persist long after their visible trails have faded, leaving invisible traces in Earth's ionosphere that can be detected for minutes or even hours after the original meteor has vanished. These electromagnetic echoes result from the ionization trails left by meteors, interacting with Earth's magnetic field in complex ways that scientists are still working to understand completely. The phenomenon creates a hidden dimension of meteor shower activity that operates parallel to but separate from the visual displays that most observers experience. Some radio telescopes can detect these persistent signatures, from meteors too small and faint to produce visible trails, revealing that the electromagnetic effects of cosmic dust encounters extend far beyond what optical observation can capture. This radioarchaeology of meteor passages provides information about upper atmospheric conditions and electromagnetic processes that complement and extend traditional visual meteor research. Gravitational focusing effects from the sun and planets can concentrate meteor shower particles in ways that create variations in shower intensity that unfold over periods longer than human observation records, requiring computer modeling to understand fully. These gravitational influences act like invisible lenses in space, bending the paths of cosmic dust particles and sometimes concentrating them into denser streams that produce enhanced displays when Earth encounters them. Jupiter's massive gravitational field plays a particularly important role in reshaping debris streams, sometimes deflecting particles toward Earth's orbital path, and other times scattering them away from our planet entirely. The complex dance of gravitational influences means that meteor shower predictions must account for the positions and movements of multiple planets, making accurate long-term forecasting a sophisticated exercise in celestial mechanics that requires powerful computers to calculate properly. These gravitational effects unfold so slowly that their full impact may not be apparent until decades or centuries have passed, creating mystery layers of in-meteor shower behavior that add elements of unpredictability to otherwise reliable cosmic clockwork. The chemical composition of meteor shower debris reflects the thermal history of the outer solar system, with different types of particles preserving evidence of the temperature and radiation conditions that existed in various regions when the solar system was young. Particles from the inner parts of comet nuclei carry signatures of heating and chemical processing that occurred when their parent bodies approached the sun, while outer layers preserve more primitive compositions that date back to the solar system's formation. This chemical archaeology allows scientists to reconstruct the thermal evolution of individual comets and infer details about solar radiation levels during different periods of solar system history. Some organic compounds found in meteor shower particles may represent the earliest forms of carbon chemistry that existed before life appeared on Earth, making these cosmic visitors potential carriers of the molecular precursors that eventually led to biological processes. The study of meteor chemistry therefore provides insights not only into solar system formation, but also into the cosmic processes that may have contributed to the emergence of life on our planet. Atmospheric tides caused by solar heating create subtle but measurable effects on meteor appearance that vary throughout the day and night, with particles encountering slightly different atmospheric conditions depending on when they arrive. These invisible atmospheric motions follow predictable patterns based on solar heating and Earth's rotation, creating pressure waves that propagate through the upper atmosphere like slow, massive versions of ocean tides. Meteors entering during different phases of these atmospheric cycles can appear brighter or dimmer than expected, with the variations so subtle that they require careful statistical analysis of large numbers of observations to detect. The pre-dawn hours often provide the most stable atmospheric conditions for meteor observation, not just because of darkness, but also because atmospheric tides reach their quietest phase during these early morning periods. Understanding these atmospheric rhythms adds another layer of complexity to meteor shower prediction and observation, revealing that even the thin air of the upper atmosphere has its own daily cycles that influence cosmic phenomena. Seasonal changes in Earth's orbital velocity create variations in the relative speeds at which our planet encounters different debris streams, affecting both the brightness and duration of meteor trails in ways that experienced observers learn to recognize. During certain times of year, Earth moves faster in its orbit around the Sun, increasing the collision velocities with cosmic particles and creating more energetic atmospheric encounters that produce brighter meteors. These orbital mechanics effects mean that identical particles can create different visual displays depending on when during the year Earth encounters them, with some seasonal showers naturally producing more spectacular displays than others due purely to geometry and orbital dynamics. The variations are subtle but consistent, creating patterns that dedicated meteor observers notice after years of watching the same annual showers under different conditions. This connection between planetary orbital mechanics and meteor appearance demonstrates how even the most basic astronomical phenomena involve complex interactions between multiple celestial bodies moving through space in precisely coordinated patterns. Micrometeorite collection efforts have revealed that Earth continuously accumulates cosmic dust at rates much higher than previously suspected, with the planet gaining several tons of extraterrestrial material every day from sources ranging from comet debris to asteroid fragments. This constant rain of space dust includes particles too small to create visible meteor trails, but large enough to survive atmospheric entry and settle slowly toward Earth's surface over periods of weeks or months. Specialized collection techniques using aircraft, balloons, and ground-based sampling methods have recovered thousands of these microscopic cosmic visitors, providing direct samples of solar system materials that complement the indirect information obtained from visible meteor observations. Some of these micrometeorites preserve organic compounds in water that may have contributed to the development of life on early Earth, making the ongoing cosmic dust accumulation process relevant to understanding biological as well as astronomical processes. The realization that Earth constant gains mass through this gentle cosmic rain adds perspective to meteor shower observations, showing that the visible displays represent only the most dramatic examples of a continuous process that connects our planet to the broader solar system. Advanced imaging techniques have revealed that some meteor trails contain internal structure invisible to casual observation, with density variations and chemical gradients that create subtle patterns within the luminous columns left by cosmic particles. High-speed photography can capture the formation and evolution of these internal structures, showing how shock waves and turbulence within meteor trails create temporary formations that last only fractions of seconds before dispersing. These detailed studies have revealed that meteor trails are not simple glowing tubes, but complex fluid dynamic phenomena with internal currents, temperature gradients, and chemical variations that reflect the detailed physics of hypersonic atmospheric entry. Spectroscopic analysis of different parts of Indivi. Ijewel meteor trails can reveal how various elements distribute themselves during the vaporization process, providing insights into the original structure and composition of the cosmic particles before they encountered Earth's atmosphere. This microscopic view of meteor formation processes adds layers of complexity and beauty to phenomena that already seem magical when viewed with naked eyes under starry skies. Cultural astronomy traditions from around the world have developed sophisticated methods for predicting and interpreting meteor shower activity using observations and knowledge systems that complement modern scientific approaches while offering different perspectives on the meaning and significance of cosmic events. Indigenous observers in various parts of the world develop techniques for correlating meteor shower timing with seasonal changes, weather patterns, and biological cycles that provided practical information for agricultural and hunting activities. These traditional knowledge systems often include detailed observations of meteor shower variations that extend back much further than written scientific records, preserving information about long-term changes in cosmic debris stream behavior. Some cultural interpretations of meteor showers emphasize their connections to spiritual or ceremonial cycles, viewing these cosmic events as part of larger patterns that link earthly and celestial phenomena in ways that modern astronomy is only beginning to understand scientifically. The integration of traditional knowledge with contemporary meteor research creates opportunities for more complete understanding of these cosmic phenomena, while honoring the human cultural heritage associated with skywatching. Meteor shower debris undergoes complex chemical changes during atmospheric entry that can create temporary compounds and molecular structures that exist nowhere else in nature, making each shooting star a brief laboratory for exotic chemistry experiments. The extreme temperatures and pressures generated during meteor vaporization can force chemical reactions between elements that would never interact under normal terrestrial conditions, creating fleeting moments when unusual molecular combinations flash into existence before dispersing into the surrounding atmosphere. Some of these exotic compounds may have properties that could be useful for material science or other applications, but they exist for such brief periods that studying them requires sophisticated techniques and precise timing. The chemical diversity found in meteor shower particles reflects the varied compositions of their parent comets, with each debris stream carrying its own characteristic mixture of elements and compounds that create distinctive spectroscopic signatures. This cosmic chemistry adds intellectual depth to meteor watching, knowing that each shooting star represents not just a beautiful light show, but also a unique chemical experiment occurring in the upper atmosphere. Long-term variations in meteor shower activity reflect the ongoing evolution of the solar system itself, with changes in planetary positions, solar radiation levels, and interstellar influences creating subtle modifications in debris stream behavior that unfold over thousands of years. Computer models can now simulate these long-term evolutionary processes, showing how meteor showers that appear constant on human timescales actually represent dynamic systems that change gradually in response to gravitational perturbations and other astronomical influences. Some debris streams show evidence of periodic enhancement and decline that correlates with the orbital periods of major planets, suggesting that the outer giants of our solar system play important roles in shaping the cosmic dust environment that Earth encounters. These evolutionary processes operate on timescales so long that their effects can only be detected by comparing observations separated by decades or centuries, requiring international cooperation and long-term data preservation efforts to understand fully. The realization that meteor showers themselves evolve over cosmic time adds temporal depth to these phenomena, connecting each year's displays to vast astronomical processes that began billions of years ago and will continue long after human civilization has ended. The interaction between meteor trails and Earth's magnetic field creates subtle electromagnetic effects that can influence radio propagation, satellite operations, and even the behavior of the aurora in ways that demonstrate the interconnected nature of atmospheric and space physics phenomena. Meteor ionization trails can act as temporary radio reflectors that redirect signals in unexpected directions, sometimes allowing distant radio transmissions to be received in locations where they would normally be blocked by Earth's curvature. These effects are most pronounced during intense meteor showers, when multiple ionization trails create complex patterns of electromagnetic interference and enhancement throughout the upper atmosphere. Some researchers have proposed using meteor trail reflections for communication purposes, taking advantage of the natural radio-reflecting properties of ionized meteor paths to enable communications that would otherwise be impossible. The electromagnetic signatures of meteors can persist much longer than their visible trails, creating invisible evidence of cosmic particle encounters that continues to influence atmospheric conditions for minutes or even hours after the original shooting stars have faded from view. Advanced computer simulations of meteor shower encounters have revealed that Earth's atmosphere acts like a cosmic filter, selectively allowing certain types of particles to reach the ground, while completely vaporizing others based on their size, composition, and entry angle. This filtering effect means that recovered meteorites represent only a small and somewhat biased sample of the cosmic material that actually enters Earth's atmosphere, with most organic compounds and volatile materials being destroyed during the high-temperature entry process. The atmospheric filtering also affects the visual characteristics of meteor showers, with harder, denser particles more likely to survive long enough to create bright fireballs, while softer materials produce the gentler streaks that make up the majority of shower activity. Understanding this filtering process helps scientists interpret both meteorite compositions and visual meteor observations more accurately, recognizing that each type of evidence provides information about different aspects of the original cosmic debris. The atmosphere's role as a selective barrier between Earth and space adds another layer of complexity to meteor shower science, while highlighting the protective function that our planet's gaseous envelope serves in shielding the surface from the constant bombardment of cosmic particles. And so our gentle journey through the cosmos draws to a close, carried on the invisible currents of ancient starlight and cosmic dust that have been falling silently through the darkness for billions of years. We've wandered together through the hidden stories written in meteor trails, from the predictable return of celestial friends like the Perseids and Geminids, to the complex chemistry experiments that unfold in split seconds dozens of miles above our heads. Each shooting star we've explored tonight carries within it tales of distant comets, gravitational dances between planets, and the patient rhythms of a universe that keeps time not in human schedules, but in the gentle clockwork of orbital mechanics. Perhaps what's most beautiful about meteor showers is how they connect us across time and space, linking our quiet moments of wonder to countless generations who have lain under these same stars, watching these same cosmic visitors paint their brief masterpieces across the darkness. Whether you glimpse them from city streets or seek them out under the darkest skies, these messengers from the outer reaches of our solar system remind us that we're all passengers aboard a planet sailing through streams of ancient stardust, collecting cosmic souvenirs from journeys that began long before Earth existed. The next time you find yourself under a starry sky, remember that you're witnessing one of the universe's most gentle performances, a silent symphony of light where particles smaller than grains of sand transform into moments of beauty visible from hundreds of miles away. Let these cosmic visitors carry you into peaceful rest, knowing that somewhere above, the ancient dance continues, patient and eternal as the stars themselves. Sweet dreams, and may your nights be filled with falling stars.